So this is, I believe, our last lesson in our unit on functions, and we're going to talk about inverse functions and specifically the properties of inverses and how you can tell if a function has an inverse. We're going to go a lot deeper than we did in Algebra 2, so hang on to your hats here. Here we go. If I can get my tablet to work. There we go. So this graphic is from our textbook, and it says the relation in Table A. The relation shown in Table A is the inverse relation of Table B. So one thing you might remember from algebra is that the domain and range switch for inverse functions, and basically an inverse function is the exact algebraic opposite of the original function. So where one would add, the other one would subtract, and vice versa. So since domain and range switch, that's because the x's and y's have switched. We're also going to notice a few other things that are true about inverse functions and their originals, is that they are reflections of each other across the line y equals x, which is the identity function. And you will notice that, like, for instance, this ordered pair on the blue function is the ordered pair 3, 4, which tells me his inverse must have the point 4, 3 somewhere there. So 1, 2, 3, 4, yep, right here. So these are reflections of each other across that line y equals x. It's a little difficult for kids to graph inverses unless you know ordered pairs. It's hard for a lot of kids to visualize like what that reflection would look like. So we just have to understand that all these properties of inverses and originals are kind of related to each other. What we have to remember is a little bit of notation. When I'm referring to the inverse function, they're going to write a notation that looks like this, or they're often going to write it like this. And this stands for the inverse function. It does not mean reciprocal. Okay, so write yourself a big note and say it is not the reciprocal. A lot of kids read that and think it means like, I'm just going to take whatever the function is and like throw it in the denominator with a 1 over it, and then it's the same thing. Totally not the same thing at all. And when we move on to the trig part of pre-calc, we're going to see the concept of inverses popping up quite a bit. So big note here, not all functions have inverse functions. You can find an inverse, but it would be an inverse relation in that case and not a function necessarily. And we're going to talk about not just the vertical line test, but also we're going to remind you what the horizontal line test means and what happens when you have a function who passes both horizontal and vertical line tests. So if you remember back from the original learnings about functions, is if you had a relation graphed and you said, oh, is this a function? The definition was that every value for x only had one corresponding y value. In other words, it passed the vertical line test. Well, it turns out if you want to know if somebody has an inverse function, you just have to know if he passes the horizontal line test. So the idea is that if a graph passes the horizontal line test, then he has an inverse that is a function. So you don't even have to know what the inverse looks like. You just have to know whether it's a function or not. And that's actually one of the first steps, is when they say, determine if an inverse function exists, and then if it exists, please find it. So sometimes you'll look out and there is no inverse function, therefore we don't even have to find it. So yay for that. So here's an example of an exponential growth, but whatever. And it definitely passes the horizontal line test, which means that whatever his inverse looks like, a logarithm, is also a function. So you probably saw that back in algebra. Hopefully that's a little bit of a review. So on to our notes here. The blah, blah, blah. Okay, inverse. And where are we at? Two relations are inverse relations. And if and only if one relation contains an element of BA, wherever the other relation contains an element of AB. Okay, so basically they're saying the x and y switch. If the inverse of the function is also a function, then the inverse is notated by that function notation. So this is a bit of a picky math teacher thing. If you're finding an inverse, but it's not a function, so like for instance, let's say you were trying to find the inverse of a quadratic function. If you have not limited the domain, which we'll talk about later, technically his inverse is not a function, because his inverse would be, ooh, not that, a sideways parabola, which is not a function, right? So you wouldn't be able to call that f to the negative 1 of x because it's not a function. You'd have to notate it some other way. And in most cases for pre-calc, we would have to what we call limit the domain or restrict the domain, so that way what we do come up with is an inverse function. We're not actually interested in anything unless it's an inverse function. Keep that in mind. A function has an inverse if and only if each horizontal line, okay, so they're going on and on about the horizontal line test. If a function passes the horizontal line test, and because they said it's a function, so that means it also passes the vertical line test, then we call it a one-to-one function, meaning every x matches with one y and one y matches with one x. So basically anything that passes the horizontal line and vertical line test is what we call a one-to-one function. So that's just a bit of vocab you have to remember for coming up. Graph the function with a calculator, yay. Apply the horizontal line test to determine if a function even exists, and then just say yes or no. They don't even want me to find it. Thank goodness, because it's actually really hard to find. So when I graph it on the calculator on the standard window, it graphs this little doohickey, and it kind of looks like a parabola, but it's a quartic, so it more closely resembles like a W, but it definitely fails the horizontal line. That was supposed to be horizontal. Gosh, I apologize. Okay, so anyways, there's one indication of it failing. Here's another one, fail, fail. So it fails, and if you're going to notate it with abbreviation, fails the horizontal line test. So there is no inverse function to this, which means I don't have to find it. So goodness. All right, graph the function using a calculator, and then apply the horizontal line test to determine if it exists, right? Yes or no. So if you were to graph this guy on the calculator, I just know from memory what it looks like, but you guys can go ahead and graph it. And it's going to graph, oops, a rational function. Oh, not that. Gosh, be golly. You know what? Maybe today was not the right day for me to record a lesson. I'm tired. I know I use that excuse a lot. Anyways, it has a horizontal and a vertical asymptote here, which a lot of kids get confused. They're like, oh, doesn't it fail the horizontal line test right here? No, because this branch approaches from the top, and this branch is supposed to approach from the bottom and not cross. So basically, since this passes the horizontal line test, yes, the inverse is a function. This next one, if I graphed it, would be a parabola shifted down 5, so something like this. So while the parabola is a function, that's not what they want to know. They want to know if his inverse would be a function. So he fails the horizontal line test. So the answer to this one would be a no. And then if I were to graph 1 over the square root, okay, so that would be, I don't know. Okay, I think it looks something like this. Confirm it on your calculator, but it's basically, okay, yeah, it looks like that. I don't know where it's shifted, but the idea is it's kind of like a square root graph, but something like that. Trust me, looks something totally not like that because I'm the one who graphed it. All right, so this passes the horizontal line test. So the answer to this one would be yes. All right. Now we're going to take this further in a minute, and they're going to say, does it exist? And if it does exist, please now find it. So that's actually what our goal is for today. If the function passes the horizontal line test, it is a one-to-one function, meaning it passes both the vertical line test to be a function and then also the horizontal line test, so his inverse is also a function. If function f is one-to-one and it has an inverse function such that the domain of f is equal to the range and the range is equal to the domain. So basically they're saying the domain and the range swap. That's their very fancy, convoluted, pre-calc-y way of saying that. And that makes sense, because if your x's and y's swap, wouldn't your domain and range swap? That's kind of how we find domain and range. So in order to find an inverse function algebraically, it is a hoot, right? So we have to confirm that it even exists before we do all the work, which is not difficult because we'll just graph it. And then we're going to replace y with x and x with y. So whenever they write f of x, we have to remember that that is synonymous with the variable y, the output variable. So we're basically going to swap x and y, which we've done this before in algebra. And then we need to solve for y. So we do a whole bunch of algebra. Sometimes it's easy, sometimes it's not. And then when we're all done, instead of saying like y equals the function, we're going to call it the inverse notation for function. And then this is the key. This is probably new for most of us. We do a lot of this in algebra too. or honors algebra 2 state any restrictions on the domain. So we're going to find out there are going to be cases where I have to restrict the domain so I don't have the horizontal or vertical line test failing on the inverse or the original. All right, so this one's already done for us. I hate when they do this. It's like it's a gigantic spoiler alert. So your original function is f of x equals 1/4 x plus 3, which I graphed it. It's a line. And remember, f of x is just fancy for y. So in order to find the inverse, since I know it exists, we're going to switch the x and y around, which they did right here. Okay. And then you have to solve for y, so it's in the correct algebraic form. So they subtracted the 3 over, I'm guessing. Oh no, actually, you know what? They didn't do that. They multiplied by 4 because they didn't like that fraction. So they came up with 4x equals y plus 12. And then they kind of like flipped the whole equation around so the y stayed positive. And then they brought the 12 over the 4x. So they're like 4x minus 12 equals y, and then flipped it. So anyways, it wasn't okay to say y equals 4x minus 12 because that doesn't mean anything as far as our work. We had to indicate that this was the inverse of our function f of x. So then they went back at the last minute. And instead of y equals, they put f to the negative 1 of x, which means inverse function. Well, it'd be nice if they were all that easy, right? It won't be. All right, so first, confirm if it's going to even exist, the inverse. So this is another line, so yes, it'll totally pass the horizontal line test. Keep in mind, if it's the line y equals 0, yes, that's a line, but it's, the 0 function, that is a horizontal line. So, or y equals anything. So those wouldn't happen versus, just be careful there. But this line would, and if I remember, this is really a y, right? So if I switch the x and y around, and then I solve for y, put it in the right form. So x plus 4 equals 2y, and then divide everybody by 2. You don't want to do ugly math. I mean, you do want to simplify it as much as possible. So I'm going to flip it around if you don't mind. So y equals 1/2 x plus 2 when I simplify that. And then remember, because we're trying to notate this to be the inverse of function f, we're going to call it inverse function f of x equals 1/2 x plus 2. I know I let my algebra 2 kids get away with putting y inverse like that. That's really only okay if they call the original problem y equals, and even then it's not okay because they should refer to them as functions since we're finding the inverse function, Anywho, if I graph this guy, parabola, somewhere over here, not really there because I can't graph. But anyways, it's going to fail the horizontal line test. So the function does not exist. The inverse function, excuse me. The inverse function does not exist. So since it doesn't exist, we'll have to do it. Now, had they restricted our domain, like cut the parabola off at x equals 1, we could have done a little work with that, and I'll show you what that looks like later. All right, if I graph this guy, it's another one of those rational function problems. Let's see, it looks something kind of like this. I don't know exactly what it looks like, but when I graph it, it looks like this. And your, CEs do a really good job of graphing these. If you have an older graphing calculator, it's going to look like it kind of connects the asymptotes sometimes. We just have to be smarter than the technology. Technology has evolved, so these newer ones are much better. So yay, I guess. The function exists, and we get to find it. So remember, this is really a y. So when I go and switch x and y around, oops. All right, I'm about to do some ninja skill math in a minute here. Cross multiplication, eh? All right, x times y minus 2 would be xy minus 2. No, it would not. Okay, I was all confident that I was going to do this, right? Xy minus 2x, there we go, equals 5. And then there's only one y in the problem, so you just kind of have to isolate it, right? So we're going to add the 2x over. So xy equals 2x plus 5. And then divide everybody by an x. Now, this is not a line in any way. So as far as how should we simplify this, technically this is okay. You could also divide each piece by an x and call it 2 plus 5 over x. Either way, we have to go back and call it inverse function f of x. Something like that. Oh, that's lovely, isn't it? All right, what else? Oh, why not? So a cubic function. Ugh. Okay, so yeah, totally looks like that. So it's a cubic function. It is shifted up 4 units. It is, I will warn you, some cubic functions wiggle so much that they fail the horizontal line test, but this one's good. So let's go ahead and find it. So I'm going to switch the x and y around. So x equals y to the third power plus 4. Solve for y. So x minus 4 equals y to the third power. And then cube root both sides. Now don't forget, when you do odd roots, cube root, fifth root, so on, you do not use a plus or minus. And then the only thing I'm going to fix is I'm going to call it what it is, which is f to the negative 1 of x. Inverse function, f of x equals x cube root of x minus 4. There we go. And I have not restricted any domains on any of these. That was on purpose. These are tricky, and on the final, and on the post-test, and on like every single summative I give you probably. I don't, they're not that tricky. Like once you get the hang of it and you know what you're supposed to do, it's really not that bad. So the issue is we're going to have multiple y's around in this problem. So when I go to isolate the y, we have to kind of do some collection. I'll show you what I mean. So first step, switch the x and y. And this is where it's weird, right? Oh, gotta switch every x for a y, including this one. Okay, here comes my ninja magic. We're gonna cross multiply. So cross multiplying this diagonal gives me xy plus 4x. Look, I totally did it that time. And equals y. So you see my issue here? There's multiple y's. So if you remember back in algebra, we did these problems a lot where if your target variable, if there was multiples of them, you had to collect them together. And it'd be awesome if when you collected them, like something amazing happened. Like they collected because they're like terms. Well, here's my problem. They're not going to be like terms. Because y minus xy, that does not simplify. But there's a common y right here. So what if you factored that y out? You'd be left with 1 minus x. Interesting, huh? All right, let me get more space in the room. Now, if I said, please isolate that y, you would just divide by the 1 minus x. Okay? It's a little backwards, and I need to call it the inverse function notation. Oh, you know what else I forgot to mention at the beginning? It passed the original passed the horizontal line test. So this is a great answer. Now, you and your neighbor might have done that same problem, same method, but maybe a slightly different approach. Like for instance, right at this step, when you went to go collect the y's together, some kids subtracted the y over here and the 4x over here, and you actually ended up with this, negative 4x over x minus 1. They are the exact same thing. They're algebraically equivalent. It's just where the negative is placed in the fraction, numerator versus denominator. So don't panic if you're like looking at my answer key or the back of the book or whatever, and you're going, oh, mine looks like similar but weird. You're probably equivalent if you were careful, so don't panic. When I give like a test, my answer keys have like every single possible weird algebraic manipulation of the answer you can give. All right, let's see what else we got here. Oh, this one's fun. All right, so pretend I graphed it. Totally passes the horizontal line test. Let's find his inverse. X equals y minus 1 over 2y plus 5. All right, cross multiply because we need to kind of free up the algebra. So x times this whole quantity down here would be 2xy plus 5x. And then 1 times y minus 1 is y minus 1. So same idea. I have multiple y's hanging out in the problem. I need to group them together on one side of the equation. That same thing is going to happen where we're going to factor out the y. So me, personally, I'm going to subtract this y over here, which means I would have to subtract this 5x over here. But, you know, maybe you went a different route, and that's okay. So over here, these are not like terms, but at least they have something in common. So 2xy minus y, gone. And then gross, negative. You can say negative 1 minus 5x, that's fine. All right, so here, notice My goal is to factor a y out so I can isolate it. So factor that y out, and we're left with 2x minus 1. Don't forget a y factored out of a y is still a 1. Equals negative 1 minus 5x. Then divide both sides. I need more space again. You know, one of these days I'm just going to write smaller. We don't have to. Alright, so if I divide by 2x minus 1, changing my notation, right? That one got really big. Alright, so negative 1 minus 5x over 2x minus 1. Whoop, wants me to drag down my picture. Alright, that's a good answer. But like we said, you know, at this step right here, if you decided to group things a little differently, you would have ended up with, let me throw this out there, 5x plus 1 over 1 minus 2x. There's other variations of that algebra. You can imagine how like super fun these are to grade, right? Just be careful and show your work and try not to skip steps. I know we're in big bad pre-calc, so we feel like we shouldn't have to show any algebra steps, but this is not the case, guys. All right, inverse function has the effect of undoing another function. That's exactly what they do, actually. So sometimes when we start learning things in math, especially in Algebra 2, I don't know if it's the age or just the exploration of upper level math. It's really like your first experience with hard math, right? So kids get to ask like, why? Why do we do this? Why do we do that? And the whole point of inverse functions is to undo other functions. So every function needs to have a function to undo it algebraically. Otherwise, we wouldn't be able to do math. So the idea is, if you were to compose one function into another function, if they happen to be inverses of each other, they're going to undo each other. So what does that look like? It's super fun. Remember composition from the last unit, or the last section? If you do f of g of x, also known as fog, and you simplify the heck out of it, you're going to do a bunch of work, blah, 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 and you're going to get equals x. Basically, all the operations undid each other. But you can't stop there. You have to refer to the other direction as well. G of f, do a whole bunch of work, and then it's going to come out to equaling x. If they are inverses, this has to happen. Okay, it's one of the major properties of inverses. It's the whole point of inverses, in fact. So, this example is already done for you, which you know how I feel about that. So they did fog. This was putting g inside of f. So here's g. They put that right there. They did some math. Right here, kids kind of get confused because forget how to divide fractions, right? When you take 6 and divide it by 6 over x, remember what happens when you divide by fractions? It's really a multiplication problem of the reciprocal. So that's why they're saying it comes out to x. Check. And then this one was going the opposite direction. So they're taking f and they're putting this right there for g, inside of g. So same issue here. They took this division problem and they flipped it around to a multiplication problem. The 6's canceled and they ended up with x minus 4 plus 4, which means the 4 is canceled and they got x. I already can hear you guys complaining now. They're like, if it's gonna come out to x, why do I even have to go through it? Because this is a proof and a verification that they are inverses. Remember in geometry when you were like, why can't I just say it is? Because the whole like convincing is the proof, the verification of the evidence. Okay, so show algebraically or verify that f and g are inverses. So they're not telling you like say whether or not they're inverses. So it's not a yes or no question. You have to show the work. And we start with log. It doesn't matter which one you start with. So G, should get my colors one day. There's f. So I'm going to write down skeleton of f. Throw g inside of it. And I'm going to go to town simplifying. Ready? 2's cancel. X minus 3 is left. Still have a plus 3. What do you know, ladies and gentlemen? It equals x. So now we go the other way. And I know, guys, I can hear you. You're like, this is dumb. I can see it's going to cancel. You still got to show me. All right, so skeleton, something minus 3 over 2. And that something is 2x plus 3. All right, let's simplify this. So 2x plus 3 minus 3, they cancel, and you get 2x over x. No, you don't. You get 2x over 2, which equals x. So again, I know you guys can kind of see the writing on the wall, and you're like, oh, they're going to cancel, da da da, it is x. You still have to show it. So when in doubt, show a little more work than you normally would, and then I think you'll be safe. I know those feel pointless. All right, my favorite property of inverses are that the x's and y switch. So because of that property on the Cartesian coordinate plane, they're going to be mirrors or reflections across the line y equals x. So remember the line y equals x is the identity function right here. And they did a nice job of mapping out the reflections here. It's very difficult for kids to see that reflection, but you know, once it's drawn, it's like, boom, obvious. If we were like matching up inverses to their originals, like this wouldn't be that difficult of a question. So we're not going to do too much of that though, but it is nice. So without even knowing like the actual function, you should be able to graph its inverse on the coordinate plane. There's some problems in the book where you have to do this. So if you would like to graph the identity function, like, okay, well, I should have started with, it assumes that you can actually graph a straight line. So you're not going to be me. All right, but basically this is going to be reflection. Now, if you're really good at reflections and symmetry, you can probably figure out what this looks like. I can't. What I'm going to do is I'm going to pull ordered pairs off of the original. And I'm going to plot them in the reversed order. So this is the ordered pair, like roughly 0, 3. So my inverse would be plotting the point 3, 0. And then this is the ordered pair negative 1, 1. So my guy would be plotting 1, negative 1. If my tablet works. Ooh, okay, there we go. And then, let's see, this one, because it's on the identity line, is actually going to plot itself. And this is enough information for someone who can actually draw to graph an inverse function. And you know what, for me, that's pretty good. They are definitely symmetrical, with this line being like the folding cutting line. You know what, I'm going to call that a win. All right, this next one, same idea. If you want to graph the identity function through, you're more than welcome to. Basically, it just goes corner to corner if you have axes that are separated by the same tick marks. So 0, 0, can keep plotting. And then, where are we at here? So I think I'm going to try to kind of eyeball this one. So this looks like 520 as an ordered pair. So mine's going to be, or sorry, 25. So mine's going to be 520-ish. And then, how about, let's see, this is roughly the ordered pair 40, 10. So mine's going to be roughly 10, 40. All right. You know what? Not bad for me. Good job. Okay, so same idea. This one's going to be terrible. I'm just going to warn you. For me, maybe not for normal people. So, I have no idea what this function is, like as far as the algebraic pieces of it, but I should be able to plot some ordered pairs and reverse them. So the original has a 0, 0, which means mine also has 0, 0. There's a lot of common points because a lot of these points, well, a few of these points end up on the identity function. Like for instance, come on, pen. 1, 1 is also still going to be 1, 1. 2, 2 still going to be 2, 2. The difference is going to occur beyond that. So let's say like this ordered pair, which is 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So mine, if I get my out of the way, will be plotting, what did I just say, 2, 3, 8. So I need to plot 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3. So here's where it gets challenging. I have to make sure I mirror like all these weird little like bows. So mirror that, mirror that. That's supposed to connect. Oh boy. Oh no, I made it worse. Imagination. There, how's that? Oh, good. All right, so this is what I was alluding to earlier in the lesson. We saw that anytime our original function was a quadratic function, it was not going to pass the horizontal line test, and therefore we could not find an inverse function. However, if we restricted the domain, so we were only looking at part of the quadratic function, we could find an inverse function. Like for instance, what if I only looked at from 0 on? Okay, so what if I restricted the domain so that x's were greater than or equal to 0 only? Or you could write it in interval notation like this. If that was the case, I could totally find an inverse function for this guy because he would look like this. So let's see what happens when we do that. If we restrict the domain on the original function and then we set up to find the inverse function, here's how things change. We're going to square root both sides. And I know normally when we square root, we have to add a plus or minus in front. But in order for this to be an inverse function, we're not going to be able to do that. So call it inverse function. There you go. And that kind of makes sense because doesn't that look like the square root graph, which is exactly what it is. Excellent. So this problem, let's see how many we got left here. Oh, homework assignments next. Okay. This is a problem from your textbook, and it is the formula to convert Celsius to Fahrenheit. And then to convert Fahrenheit to Kelvin, they have another formula here. So they're asking you to look at this problem and determine what inverse of f of x represents. So if you think about the properties of inverses, it's where x's and y's switch, right? So if I take the inverse of this, where x is used to convert Celsius to Fahrenheit, right? So x represents Celsius in the original function. So if I take the inverse of that, x would now represent Fahrenheit, and then f of x in the inverse is going to represent Celsius. The next question, and you're going to do some for your homework, but it says show that f and f inverse are inverse functions. So I want you to do the composition of f of, where are we at? f of -1 and f of -1 of f. And then they want you to graph them together to show that they reflect across the line y equals x. And then they're going to want you to compose k of f and figure out what that represents. I don't want to do this problem for you. I want you to think about that one, okay? Think about what happens when you take function f and place it into the Kelvin formula. And then you're going to use that new formula to figure out if you have 60 degrees Celsius, how can you convert that to Kelvin? So the idea is rather than going from multiple scales, you can go straight from Celsius to Kelvin because of this new function that you've derived. And that's actually how they had to do this way back in the day when they were still interpreting what these different scales represented. They found relationships between them, and then they composed functions together. The point, and that's actually the end of our unit for function. Next unit is this one, so look forward to that.